about things like temperature and moisture and all of that and pressures. All of that relates to what makes the air move. Every day we walk outside and we feel a little breeze in our face or look at a leaf blowing or snow blowing. Uh, some days the winds are very light. Other days they're significantly more. And a lot of things impact the winds. So this could get a little bit more complex, but we'll try to make it as simple as possible. I wanted to just start off with just a simple weather map. It's today's weather on Saturday morning here. There's low pressure generally near my house. I've had rain all night long. And notice the pressure gradient. We've talked about the pressure gradient and how tight the pressure gradient can be or how loose it is. And under high pressure, there's not a lot of pressure gradient. Under lows, there tends to be more. Now, notice above my house here, the pressure gradient is, not strong, but enough. And we have winds. Winds are blowing from the east at 25 knots, about 30 miles an hour here. Here's 15. But look in the middle of this high where most of you guys are living. No wind. Winds are calm this morning. You just literally see a circle around the station pressure, so the station symbol. So you wind up with not much wind. So you can see lows are going to typically have more wind. Highs are going to have less. Another thing that governs winds is what type of terrain, topography they're over. So take a look, for example, these winds over the water, 25 knots, 15 to 20 knots. Come back over the land, they drop off to about 5 to 10. Water has less friction. In other words, it allows the wind to move quicker. It doesn't put any stress on those air parcels as much as land does. The same king can be held for the west coast, mountain ranges, less wind typically. And you go out all the way out west here, maybe we can get there. Not today though. But you wind up with a lot less wind sometimes in the Rocky Mountains or at the lower levels of the Rockies with the winds getting bumped around. If you go up to Lake Erie, you wind up with more winds over the water than you will over the land. And one of the things I want you to know, we're going to talk about geostrophic winds and gradient winds. Two types of winds. Gradient winds blow in a circle. Simple enough. Geostrophic winds tend to blow parallel to an isobar or contour. So if you're looking at this big high here, you'll notice the winds are coming down and around, nice clockwise pattern like you'd expect around a high. That is a gradient wind. Counterclockwise around the low here, gradient wind. Let's look above that. 300 millibars, jet stream, where the fastest winds in the atmosphere are in the wintertime. And in the summertime, they're a little bit higher up. So if they're that high, we know, for example, right now, out over California, they're getting rocked in the mountains with very heavy snow. Well, look at the very strong jet stream coming in. And those mountains are up. I mean, they're 8,000, 10,000 feet. This jet stream's probably at 25,000 feet, but still, some of that air is hitting those mountains. And what happens when the air hits the mountains? It rises. It produces precipitation. We've learned that in the last chapter. So we have one jet stream here. Notice these are pretty much parallel to these contours. Contours represent basically an isobar. Have another jet stream coming into Southern California and across the south. This is extremely typical of an El Nino pattern. You have a strong southern jet and you have another one across the north. Notice we have another stronger jet over here. We're going to talk about winds diverging this chapter too. What does that mean? Well, take a look right here. I have a 80 knot, 90 knot wind right here. Right behind it, I have a 60 knot wind. What happened over this area right here? the winds are being pulled apart. So I have divergence. Divergence is just that. Winds are pulling apart the air. Convergence, on the other hand, winds are pushing the air together. So in this map, yellow literally represents divergence. So I have pretty good divergence. That's now up over Pennsylvania, and we looked back. We saw rain up there. We also had the low pressure. Think about it. Air is a continuous fluid. So it starts all the way down at the ground and moves all the way up through the atmosphere. So if I am pulling the air apart up in the upper atmosphere, something has got to come take its place, so the air below it's going to rise up and take that place. That means at the ground, oh yeah, atmosphere doesn't like a vacuum. It's not going to want to go there. So the air is going to come together. So we wind up with convergence at the ground. So when you have divergence aloft, you probably have convergence at the ground. When you have convergence aloft, which typically happens big high pressure systems here, 55, 60 knot winds, and here you go down to 35. So you have convergence. You're pushing the air down, you're sinking. You wind up with divergence at the ground. Divergence at the ground means the air is spreading apart, light winds, nice weather. So now you've just seen an overview of applying what we're going to look about here. And we're talking about the atmosphere and the winds. Now let's go into a little more detail. So, all right. So we go up here, and we'll look at this as a slideshow. We're talking about winds and weather. And what forces control the speed and direction of the wind? So we talked about some of that. What is a force first? All right, if I pushed on your car with my hands in the back of your car trying to move it because it's stalled, that's a force. If I'm throwing a rock, that's a force, or a baseball. All things that cause something to move from at rest is a force. And force is just mass. So in other words, the more material you have times the faster that material is. So if I could shoot something at the speed of light and have a pretty good amount of material with it, I would have a heck of a force. We don't do that, but that's what we're talking about here on forces. So with that, there's a couple other things that apply to winds here. We're going to talk about air pressure gradient. We talked some about centripetal force, another interesting one, Coriolis effect, friction, all those. So the closer the isobars together, we've already talked about this, the more the pressure gradient is, and this is the strongest influence on winds. So the tighter that you look at a weather map, if you see pressure isobars fairly far apart, you're not going to get a lot of wind. If they're coming closer together, the winds are going to increase. When you look at a hurricane, the isobars are very, very close together near the eye. That is why there are such extremely strong winds there. And now, another force, centripetal force. Well, if you're moving in a circle, if you go around a corner in a car, if you're throwing a discus like this, all of these things you're curving around. Something is keeping that car on your path. That's centripetal force. It's an opposite force to where you want to go. If it wasn't existing, if it didn't exist, you just keep going straight and right over the cliff that your car was going on the non-curvy road. So it's always exerting to make the object that it's pulling on to go in a circle. So when you look at low pressures and high pressures on weather maps, and you'll notice the wind going in big circles around them, this is a centripetal force. Look at a tornado. The winds go very quickly in a local area. That's centripetal force making them go in that circle. That and the pressure gradient combined. Two forces. So there's one more force we need to start getting into a little bit. Coriolis effect. This only occurs on a rotating planet, or Earth in our case. The Earth rotates. Think about it. The circumference of the Earth is much bigger at the equator than it is obviously at the North Pole or South Pole, right? So in order, we know that the planet goes around in 24 hours, makes a complete revolution. So which part of the planet is going to move faster relative to the outside frame of reference? Well, obviously down towards the equator is going to move much faster, right? So that, because of that difference in motion, it actually generates a force on the wind. It's called the Coriolis effect. It occurs in the northern hemisphere and always pushes the wind, the air parcels, to the right. In the southern hemisphere, it will push them to the left. And the deflection is always strongest, maximum at the poles. The least deflection occurs at the equator. So, literally, there is no Coriolis force at the equator. The strongest Coriolis force will increase as you go towards the poles. So there will be more and more deflection. If you were to shoot a pool ball, and I've heard this in discussions and seen it written up in papers, some of the best pool players in the world, when they go and travel, they have to take this into account because literally the pool ball will curve more the further north you are than if you're near the equator. So there's literally a slight shift to that pool ball because of this force. That slight shift could make all the difference in you pocketing that ball or not. Friction is another force. Obviously, the ground is going to cause the most friction. So, big objects on the ground like buildings, say you have mountain ranges or hilly terrain, all of that's going to have the most friction. Flat surfaces like water are going to have less friction. So there is your friction at the ground. Now, because it's a fluid, the atmosphere is a fluid, there's going to be what they call eddies. So while most of the friction is going to occur in the first 3,000 to 4,000 feet, there's going to be some friction that occurs through turbulence higher up in the atmosphere. That friction is what makes your plane bump sometimes when you're flying along. That is turbulence. Turbulence is one of the hardest things to quantify. Matter of fact, it's one of the equations that does not quantify, that we can't solve. One more force, gravity. Gravity always works to pull everything down to the ground. Gravity will only impact vertical motion. It does not impact horizontal motion. So it is always going to tend to pull things to the ground. On Earth, because we rotate, it is two things. You have the centripetal force, which is tending to keep objects pulled toward the ground, and gravitation. Yes, centripetal is much, much less, but they work together. And you will probably see that in the question. So now we've got all these wonderful forces working. So let's just look at a little tiny air bubble, an air parcel of air. I don't care what kinds you call it. If I know I have vertical pressure gradient, and we know we do, we've talked about it, the pressure decreases significantly with height. Matter of fact, the strongest pressure gradients on Earth are in the vertical. So with that, why the heck is our atmosphere still here? Our atmosphere is still here because of gravity. Gravity is pulling those air parcels down. And there's a balance. In that balance, we're just saying that hydrostatic equilibrium means gravity and air pressure are balanced. The pressure gradient, force, and gravity have reached a balance. So if that air parcel is standing perfectly still in the atmosphere, it's balanced. Now, yes, if that air parcel is moving along and hits a mountain range and pops up, it still can be in perfect balance as long as it's not accelerating. It'll just move at a constant rate upwards. So that, or downwards on the other side of the mountain. That is what's hydrostatic equilibrium. It only impacts vertical motion. Geostrophic wind. I talked about that some earlier. This is another way we try to simplify things. We're just looking at two pressure gradient forces here. We're looking at Coriolis effect and horizontal pressure gradient. So, say an air parcel starts out with a pressure gradient pushing it across, like here. We see this little pressure gradient here. It's pushing this air parcel to go that way. Coriolis force is beginning to turn it to the right. So instead of going straight, it's going a little bit at an angle. With time, the two forces become balanced because your velocity is increased and Coriolis force gets stronger with the faster velocity so that you reach a balance. That is when the wind is going parallel to the isobars or contours. If they're going parallel, these are geostrophic winds. They're not going in a circle, they're going parallel. Perfectly straight. Gradient winds add one more force. All the gradient wind is you're adding centripetal. That causes the air parcel to turn, constantly rotating the air parcel in a circle. Friction, mainly down towards the ground, closer to the ground, the more it's going to impact. So if I have friction, I have it down towards the ground. What's it doing? It's slowing velocity. It's slowing the wind. So now I have an imbalance with the Coriolis effect. What that means is that on high pressure, it tends to have divergence, tends to pull the winds away from the highs. Instead of moving directly in towards a high, they're going to tend to want to go or diverge away from the high. On the low pressure, on the other hand, they're going to tend to pull it in, converge. They kind of tend to cross the isobars at slightly different angles because of that. Instead of going straight across or straight parallel, they're going to move at an angle. That's what friction does. So now you've seen all these wonderful forces messed up. That's why we get the winds we get. That's if you looked outside today and said, oh boy, the winds are blowing this way. All these forces combined to make that happen. We talked about it being the continuity of wind. If I have divergence at the ground, I have sinking air. If I have convergence aloft, I'm tending to push the air down. High pressure. Same exact thing for low pressure, except the opposites. Lakes. All right, if I have a wind blowing across Lake Erie from the north, that wind's going to be picking up speed as it's moving across Lake Erie because Lake Erie is very smooth. Now, south side of Lake Erie, there's a couple hills in Pennsylvania I know of. I'm not sure about Ohio, but I know there's a few in Pennsylvania. What happens? That wind's going to slow down, right? So if it's slowing down, what is happening to the air? It's being forced to rise. If it's rising, we have rising air causing condensation, maybe even causing instability with that condensation. That's where you're getting your lake effect snow showers from. So the fact that your wind is moving across the lake with very little friction, then the friction's increasing, begins to lift the air, and you wind up getting snow showers. So that's what I wanted to talk about today. I hope you got something out of that. Please don't hesitate to ask if you have any questions.